Hello dear students, welcome to the channel and very welcome to this playlist in which we are discussing about corona, overvoltages in power system and transients in power system. So we have already covered corona and overvoltages in power system part, and now we are discussing the transients in the power system. And that too we have discussed a lot of things in previous videos. So in previous videos up till now we have seen that what happens when a transient situation occurs in this simple RL circuit. We have seen the transient in simple circuit. We have seen what happens to uh, alternator when suddenly short circuit applies on it. We have done its analysis, and then we have seen arcing grounds in previous class. We have also seen capacitance switching, current chopping, and wave equation in previous class. And in the last topic, we discussed about the traveling wave on transmission line with its specifications and its shape. And continuing that, today we are going to discuss about the reflection and refraction at T junction. So, as we were discussing in previous class, the reflection and refraction of the surges or waves are produced at the junctions at a terminal in your line, and the impedance will suddenly change at the junction points and even the at loading points as well. So the line cable junctions and even the fault will constitute such discontinuities. And now independent waves will meet along the line with the combined accordance with the polarity to provide different voltages and current levels at the meeting point. So what happens here is, see this image here. The forward waves of the current and voltages are given by same polarities. If the wave is being reflected, the corresponding current and voltage waves are given opposite polarity, right? So the forward current waves and forward voltage waves will have same polarity, and if wave is being reflected the corresponding current and voltage waves, then opposite polarity. Now wave of the current and voltage will be transmitted along the line of characteristic impedance ZC, which is terminated by the impedance Z. As you can see here, ZC is terminated by impedance Z. Now let's see different relations of voltage, currents, and impedance and coefficients. So E and I, basically voltage and current, will represent incident waves, and ET and IT will represent the transmitted waves. And transmitted waves are same as the refracted waves. Okay, and notice here I'm not saying reflected, I'm saying refracted. Okay, they are refracted waves. So here you can see E and I, whereas in datum you can see ER and IR, they are refracted. Okay, ER and IR are refracted, and the junction ZC will be remain as it is. So ER and IR represents the reflected waves. As you can see here, ER and IR are reflected waves, and ET and IT are transmitted or refracted waves. Okay, we will see it further. That will be refracted waves. Now my original, which means incident, then transmitted, which is refracted, and the reflected voltage and current can be written using these formulas given here. E equal to I into ZC, which is for incident. ET is equals to IT into ZC, which is for refracted or transmitted, and ER equal to minus IR into ZC for reflected. And why minus? Because it is reflected, right? And in reflected, what did we do? We took opposite values, right? See, they are opposite in values. So negative sign because ER and IR are traveling in the negative direction of X, which means backwards on the same line. So basically the transmitted voltage or transmitted potential will be basically the sum of my incident and my reflected potential, which means ET will be equal to E plus ER. And same ways I can say for the current, that transmitted current or the refracted current will be the sum of reflected current and incident current. Now based on these equations, we also know that from these equations, if I make I the subject, then I will be E by ZC. So we have written it here. Same ways IT will be ET by Z, and minus IR or IR will be minus ER divided by ZC. Correct? We just made I the subject. Now when we put these values of I in this formula, the formula will look something like this. ET by Z, which is basically value of IT, will be equal to E by ZC, which is basically value of I, and ER by ZC, which is basic value of IR. Notice here we are having minus sign instead of plus sign here. That is because of this minus sign here. And when you from other two equations, let me tell you which two equations. The equation of the voltage, and based on this equation of currents, we can write ET by Z will be equal to E divided by ZC minus ET minus E, because what is the value of ER, right? ER is basically ET minus E. See here, ER is basically ET minus E, so you can write it. So we'll write ER equal to ET minus E divided by ZC, so that just so that we can get ZC as common denominator. And then what we will do, we will make E the subject, right? So by making E subject, what we will get the term which will look like this: ET 1 plus ZC by Z equal to 2E, which means ET will be E into 2Z divided by Z plus ZC, taking LCM on this side, right? And then taking the whole term on the other side. So this is the equation for ET. ET equal to E into 2Z divided by Z plus ZC. Then for IT will be equal to ET divided by Z, right? Now you know what is the value of ET, so just substitute the value of ET and then divide the whole term by Z. Now you already have the value Z in in the value of your ET, so will get cancelled, and what you will have 2E divided by Z plus ZC, right? You can write 2E divided by Z plus ZC. But now see again, what is the value of E initially? I into ZC. So you will write simply ZC into I, which means instead of E you are substituting I into ZC here, and the rest of the terms will remain as it is. And that is the formula for your IT in terms of I, right? You can find the ET in terms of E, and you can also find IT in terms of I. And same ways now you can do the same for ER and IR, which we did here. See, ER was basically ET minus E. So what did we do? We just substituted the value of ET, right? We simply substituted value of ET here. The T will not be this big T, it will be subscript here. There is a mistake in printing, so it will be 2ZE divided by Z plus ZC minus E. And when you do so, the final value of ER will be E into Z minus ZC divided by Z plus ZC. Same ways you can calculate for IR as well. Basic value of IR is equals to minus ER divided by ZC. So uh, what you can do, you can substitute the value of minus ER here, You have already calculated the value of ET, you have already calculated value of IT, you have already calculated value of ER as well, right? See here you have the value of ER. So what you can do here, you can simply substitute the value of ER, which is E into Z minus ZC divided by Z plus ZC. So you will just simply write it minus E Z minus ZC divided by Z plus ZC. Minus will be here because of this minus, and then the whole term divided by ZC as it was earlier. Now see one thing, that what is the value of minus E divided by ZC. See here, minus E divided by ZC, it would be minus I, right? Minus E divided by ZC would be minus I. So this minus and the minus which we will get from minus I will get cancelled. So minus minus will get cancelled and we will be left with I into ZC minus Z divided by ZC plus Z. And that would be the value of your IR in terms of I. So this is how you will derive the values for all transmitted, incident and reflected waves. Now this coefficient 2z divided by z plus zc, then z minus zc divided by zc plus z, this all coefficient apologies, this all coefficients are called coefficient of reflection and coefficient of refraction. Okay, based on with which entity they are getting paired with, they are called coefficient of refraction and coefficient of reflection. 2z divided by z plus zc is basically coefficient of refraction, and z minus zc divided by zc plus z, that is basically coefficient of reflection, as it is getting multiplied with reflection here, right? And because it was getting associated with refraction, it will be coefficient of refraction. Now from these derived terms, we can what we can do, that we can follow things which we can note down, right? Like transmitted or refracted current or refracted voltage will always have positive polarity, if you have noticed here, right? It always had the positive polarity. Now polarity of reflected wave, the reflected, I'm saying reflected wave, will be depending upon the magnitude relationships between zc and z. And if zc will be greater than z, then the voltage wave will be negative and the current wave will be positive. And if z will be greater than zc, which is opposite of previous, then the voltage will be positive and the current will be negative, right? So this is your refraction at T junction. Now we are going to talk about the typical cases of line terminations, right? So there are so many ways that my transmission line can get terminated, and majorly there are typically four cases or four scenarios which are responsible for the termination of line. The first one is called the open circuit line, second one is of course short circuited line, third one line terminated by an impedance, which is a very interesting one, we will talk about it, and the fourth one is the line connected to the cable. Now let's discuss first among them the case of open circuited. Now here see, we are having E and I, which means my intermittent signals. Then we am having reflecting signals ER plus E, and I'm having IR, right? So we can see the reflection of wave in open circuited line. Now the line is open at receiving end, so the impedance, what will be impedance? If my line is open, then what will be the value of impedance? It will be infinite, of course. So the impedance will be infinite. The value of ET will be 2E because of the doubling effect, because ER and E both are getting added with each other. So ET will be 2E. Now as my line is open circuited, what will be the value of current? It will be 0. The value of ER, interesting enough, it will become same as E, and the value of IR will become negative I. And in order to satisfy the boundary condition of an open circuit, when incident current wave I arrives at an open circuit, then the naturally reflected wave is at once initialized as equals to minus I, which means they are in opposite directions. See, I is in this direction, so IR in the opposite direction. So they are in the opposite direction, whereas voltages are added up with each other, right? So that is what happens actually in short circuit as well. Sorry, that is what happens actually in the open circuit as well. Current, because I and I are in the opposite direction, the resultant will be zero, but the voltage will be maximum. That is what happens in the open circuit as per our basic understanding. Now let's see the second case of short circuit. So see here what is happening in short circuit. E is getting ER, but the ER is in the opposite direction, where IR and I are getting added. See, my line is short circuited at the receiving end, so value of impedance will be of course 0, and the transmitted and reflected waves can be given as Et equals to 0. Why Et is equals to 0? Because E and ER both are in the opposite direction, so their resultant will be 0. It will be equal to 2I, which means IR plus I, and if the value of Et equal to 2I, which means IR and I both are equal, right? IR and I both are equal. ER and E will be equal, but because they are in opposite side and cancelling each other's effect, that means they are equal and opposite, so ER equals to minus E. So we all know at short circuit what happens, voltage is always 0, so you are having Et 0, right? Because E and ER are cancelling out each other. And what is the value of current? Current is always maximum, so you are having IR plus I added up with each other. Now in order to satisfy this incident, this uh, this scenario, the incident voltage E will be arriving at the short circuit, so the reflected wave must be equal to the E, as you can see here in this image. Then there is the third case, which is basically the case of line terminated through the resistance. So what happens in that case? See, in case of the line terminated through the resistance, the value of Z will not be 0 and it will not be infinite, like the cases of open circuit and short circuit, right? There will be some value of my impedance, and what will be the value of impedance? It will be ZC. The value of Et will be E and It will be I, basic and simple. Value of ER will be 0, which means there is no reflection. Value of IR will be 0, so in current and voltage there is no reflection at all. And what does it shows? It shows you that the line is correctly terminated. So when you don't have any reflection, that means your line is correctly terminated, and that is why Et will be equal to E and It will be equal to I. Now the fourth case, when line is terminated to a cable. Now we all know that it is advantageous to connect a cable to the terminating overhead line near my station. Now why? Because because of the capacitance of this cable, the advantage is that the voltage entering at the cable from overhead line is only 20% of incident voltage, right? Because the capacitance of my cable will give the advantage, and the voltage entering at the cable from overhead line will be only 20% of the incident voltage. Also it reduces the steepness of my wave, right? It will make it less steepen and more balanced, right? When we reduce the steepness, then we reduce the voltage distribution along the equipment winding, right? It makes my voltage more smoother. Now see the image here. We are having Z1 and Z2 at different impedances. You are having overhead line here and cable here. This is Z1 and this is Z2. So it suffers refraction and reflection at the cable junction. Okay. So the refracted voltage is given using ET here, 2 Z2E divided by Z1 plus Z2, and the surge impedance is also given to you. It is 500 ohms of overhead line and only 50 ohm to of the cable. Okay, these are the approximate values. So when we calculate the value of ET, it would come around 20% of incident values. So that is what I was telling you. So you have to be very careful while selecting the length of the cable. It should not be shorter than the expected length of the wave, and if it is shorter than the successive reflection at the junction are caused in piling up, the voltage may attain the level of incident voltage, right? So if my voltage will attain the level of incident voltage, then the condition can be tricky or dangerous for us, right? Now except for these, there are one or two more other interesting phenomena, like line that terminates through the capacitance, right? See this image, the image on the left hand side, and consider the capacitance connected so far end to the line, and the line has the DC surge to infinite length traveling through it, right? Line is having a DC surge of infinite length traveling through it. Now the surge impedance of the line will be Z, and the reflected voltage or voltage across the capacitor can be given using the equation given here. V raised to nt will be equal to 2V into the bracket 1 minus e raised to minus t divided by Ze, and we use it to solve the problems related to the line terminated through the capacitance. And here you can see the waveform of the incident voltage and the voltage across the capacitor here. This is my incident voltage, it will be flat straight, and here I'm having the voltage across the capacitor, which is slowly gradually rising, and it will once attaining saturation, it is staying as it is. Then capacitor can also be connected at T. As you can see here, I'm having Z1 Z2 and then I'm having capacitor connected here. So a T junction where capacitor can be connected, and the voltage across this capacitor at T junction can be given using the formula like this: 2V Z2 Z divided by Z1 plus Z2, 1 minus exponential minus Z1 plus Z2 divided by Z1 Z2 C into T. That would be the formula. And the derivation for traveling surge is worked out considering finite duration of my surge, right? So the derivation for traveling surge is worked out considering only a small finite duration of the surge, cannot go till infinite value. So see this image, it is the value of the original term except exponential against time. So we are having value something like this. Now this is the magnitude, and this is the tau, the finite duration which I was talking about. This is the tau, the finite duration, and this is the magnitude of my voltage on the positive side, and this is the negative volt magnitude of voltage, right? So the wave is decomposed into two waves. F of t equal to, let me show you, f of t equal to vu of t minus vu t minus tau. Now vu t minus tau's value will differ based on what time this signal is observed. If it is observed at t greater than or equal to tau, then its value will be v. If it is observed before the t's value hits tau, then it is considered 0. So in such case you can find out the value across the capacitor using this formula you are given here. V of s will be the Laplace of f of t, which is 2 divided by z1 divided by z1 plus 1 divided by z2 plus cs, right? And when you take LCM and when you include the exponential components, when you include everything, when you take Laplace and include exponential components, because taking Laplace will include exponential components basically. So when you do so, you will get final value which looks something like this: 2v z2 divided by z1 plus z2, 1 minus exponential minus z1 plus z2 divided by z1 z2 c into t. And taking out this term zv into z2, the whole term will be negative divided by z1 plus z2. So basically this 2v got cancelled somewhere, right? No, sorry, this is there is a, I think there is a mistake. There will not be a negative sign here. There will not be equal sign here. Probably there will be negative sign, right? So what we will have, we will have 1 minus exponential minus z1 plus z2 divided by z1 z2 c t minus tau, and the final value of v and tau will look something like this. When you take t equal to tau, it would be 2v divided by z2 z1 plus z2, 1 minus exponential minus z1 plus z2 z1 z2 c into tau. So from this what we can state that, we can state that the attenuation in voltage magnitude for short wave is more rapid compared to the longer wave, right? For short wave it is more rapid, longer wave it is more smaller, as you can see here, for the as far the time goes and as far the voltage rises. So in analysis of power system, we mostly assume that the lines are lossless and they are there is no distortion or attenuation of my wave, right? But actually in power system there are always losses, right? Consider this losses, and we have to make the analysis, but that is a difficult task, so mostly we avoid it. But these losses are desirable as wave energy is dissipated through those losses only. And these losses occur in the system because, why? Because of the line resistance, leakage conductance, corona, all such causes. So the losses because of losses due to the line resistance are very important. Losses due to corona and high voltages are greater than the value of losses generated from the line resistance. So while travel along the line, the waves undergoes three uh, challenges which has to face. The first one, the crest of the wave is attenuated or decreased in magnitude, which means basically its magnitude gets decreased compared to its original value. Second, the wave gets elongated, its irregularities are smoothened and steepness is reduced. So if your signal was more sharp, more steep, then it gets reduced. And third, voltage and current waves cease to be similar. So you will see that voltage and current waves will never be similar for all three cases, right? For all three means your original and reflected and refracted. And at high voltages the electric field gradient in the air will increase to if it increases to critical value, the air will get ionized, and we have seen what happens in such case, right? Due to the air's ionization loss, there will be some loss, and if the potential of the line increases beyond the value of corona discharge, then corona will occur, and it will produce the ozone gas in the air surrounding the conductor, just like we saw back in the lecture when we discussed corona. So because of this corona discharge, what do you see? We see the violet glow which occurs around my conductor, and it is accompanied by what? A hissing noise, hissing sound. And this energy which is required to ionize air is supplied by what? It is supplied by waves. So the surges are unaffected till the threshold voltage is reached. Threshold by will mean threshold, I mean corona threshold, and above the value of corona threshold the effect will be pronounced. So this initial peak is removed by the time that uh, taken to travel by the wave for 2 to 3 kilometers, and after that the attenuation continues at a slightly reduced rate. So the center and the tail of the waves are built at the expense of the front. That's why the value gets decreased. Now wave attenuation because of corona is more pronounced for positive wave compared to negative wave. That is also that we discussed earlier. And why was that happening? Because of the corona loss. uh, why was that happening? It is because of greater corona loss for positive waves. Now if you want to calculate the value of attenuation, then how do you calculate it? You calculate using Faust and Manager empirical formulas. And what are these empirical formulas? So the formula is E is equals to capital E divided by 1 plus K into Ex. Small e shows you the surge voltage at distance x from origin value, and the unit of it will be in kV. E will be show you the surge voltage at origin, and unit will be kilovolt again. K will be the attenuation constant. The value of attenuation constant for shorter waves is 0.00019, which is almost 5 microsecond, and for long waves it is 0.0001, almost 20 microsecond. And the x is the distance of the distance of your transmission line in kilometer. Now the voltage wave the voltage wave I wanted to talk about before we move forward. Let me change the slide. So the voltage wave in voltage wave incident on the transmission line at an initial part where x will be 0 will travel at a velocity of v such that the later time t at an initial point x will be equal to vt from the point of the incident shown in the figure, as you can see the figure on the left hand side. And in doing so, if crest value of the voltages is higher than the corona disruptive voltage for a particular conductor, the loss of the energy will take place, and the energy will travel. Loss of energy will take place while your wave will be in the travel. And when this thing happens, the amplitude will decrease corresponding to the lower energy content as well. And also the addition to this, the attenuation or decrease in amplitude wave shape will show distortion in it. So energy distortion is actually an electromagnetic phenomena, and it is also electrostatic form. So the time rate of loss of the stored energy in such cases will be equal to the power loss which happened because of corona here. So the total energy in the differential length dx of my wave can be given using this formula here on the right hand side. You can see dw will be 1 half c dx into v square. So basically it is the sum of the energy stored in the capacitor and inductor, but we are multiplying it with dx, the distance, right? Basically dx is the this width. See, dx basically is this width, so we are multiplying it with dx. So dw equal to 1 half c into dx v square plus 1 half l into dx I square. So now that you know the values, and we have also seen in case of search traveling wave relations of VIZLC when we discussed about that, and we derived the whole term related to speed of light as well, right? When we derived the surge impedance Z equal to under root L by C, and velocity propagation V equal to 1 by under root LC. Based on that, we can say that I square will be equal to V square by Z square. And again, what are the value of my surge impedance? Z equal to under root LC. So Z square will be L divided by C. So my I square's value will be CV square divided by L. The value of dW will be C into dx into V square here. And considering the capacitor capacitance does not change, then the rate of the uh, dissipation of energy can be given using this formula here. dW by dt equal to d into c v square dx by dt. And when you take the derivation and all, then you will get 2cv into dx dv by dt. So the power loss over the differential length dx can be given using this formula, pc equals to f v into dx. So that 2cv into dv by dx will become what? It will be equal to minus pc or minus f of v, right? Now we can also have a linear relationship. So what happens in the linear relationship? Then your fv will be equal to ksv minus v0, and then the v1 will be your initial voltage. And here what you will do, you will take 2cv dv by dt equal to ksv minus v0. Now when you separate the variables using initial condition, you will get v equal to vi at t equals to 0 yields. So v minus v0, what you will get is v minus v0 e raised to v divided by v0 equal to vi minus v0 e raised to vi, which is vi which tells to t divided by v0. Sorry, not test, it was alpha. It was alpha. Vi alpha t divided by v0, where the value of alpha is ks divided by 2c, and v0 is the corona inception voltage. So similarly, this way the voltage in the axis of the corona inception at any time of t or distance x equal to vt can given using this formula, v minus v0 divided by vi minus v0 equal to e raised to vi minus v minus alpha t divided by v0. So that is your attenuation formulas of traveling waves. Though don't worry, you don't have to remember all these formulas, just understand the concept of attenuation, and I think that is more than enough. So that was that for this topic, and also for this chapter, and also for this playlist as well. So we will keep this lecture till here, and that is with this lecture, that is this is also the wrap of power system 2 coursework of GTU. So we are ending this playlist here. If you have any suggestions or any feedbacks related to the channel or videos, please feel free to mention them in the comment section below. Any doubts, you can mention your doubts, queries in the comment section as well. I will try to answer as many as possible and as much as possible as quick as possible. And if you have any recommendations for me that I should make a video on this subject, please mention that in the comment section as well, so that I can know what content that you prefer or what you want to see, right? So that's the wrap for this subject. If you have any doubts or queries, feel free to reach me out. And thank you very much for being patient and listening whole lecture. I will be seeing you next time with a new subject. The signal system playlist will continue. So thank you very much for listening and take care of yourselves. Goodbye for now.